In this lesson, we are going to find confidence intervals for population means and the means of paired differences. All right, first, let's just review what the difference is between a sample standard deviation and the standard error. So first of all, the sample standard deviation is estimated using your sample. This is an estimate of what we call sigma, which is the true standard deviation of the population. The formula used to find this is the square root of the sum xi minus x bar squared over n minus 1. We did that back in chapter 2. And this estimates how much the sample values vary relative to the mean. So, we have the whole empirical rule for this, that most sample values fall within plus or minus 2 standard deviations of the mean. Now, the standard error of x bar is found using the sample standard deviation divided by root n. This is the standard deviation of x bar, and that's not quite, it's an estimate of the standard deviation of x bar, which tells you how much the mean would vary if you took many samples of the same size and compared the means from these samples. So this measures the accuracy of your estimate for x bar. So a larger standard error means there's more wiggle room for where your x bar could have fallen, whereas a smaller standard error means that you are pretty certain you know what it is, or that your sample estimate is close. So suppose you find the mean number of hours of TV watched per day is 2, with a standard deviation of 1.5. Find the standard error of the mean and describe what it means. Assume the sample size is 165. So the standard error of x bar is s over root n, or 1.5 over root 175. Which is 0.113. And what this means is if you were to take many samples of the same size, so if you were to take many samples of a size n equals 175, and find x bar for each, the standard deviation of x bar would be about 0.113. In other words, this tells you how much x bar varies from sample to sample. So suppose you want to estimate a population mean. So the first question you're answering is that if you were to measure some quantitative variable like height, weight, something like that, what is the mean? How much is the mean going to vary across all samples of a given size? And then to address how much the mean varies, we're going to find a confidence interval estimate of the mean. And this confidence interval will give us sort of a range of plausible values for that mean. So recall that the general formula for a confidence interval is your sample statistic plus or minus some multiplier times the standard error of the sample statistic. So here our sample statistic is x bar, which is the mean or average of all of your numbers in the sample. The multiplier is Tstar, which is found using the t-table with degrees of freedom equals n minus 1, and the specified confidence level that you've been given. And the standard error of x bar is equal to s over root n, where s is the sample standard deviation, which is usually given to you, and n is the number of individuals in the sample. So first, let's find the T-star multiplier for the following sample sizes and confidence levels. So if our n is 22, remember that our degrees of freedom is 21. And if we would like a 98% confidence level, the T-star value for that is 2.52. Next one, same sample size, so same degrees of freedom, but lower confidence level. In this case, T-star is 1.72. Note that lower confidence implies a smaller multiplier. All right, now that we know the pieces, let's actually find some confidence intervals. So we know that x bar is 76, our sample standard deviation is 6, and we have a sample size of 16, and we want the 90% confidence level. So first let's find the standard error of x bar, which is s over root n, or 6 over root 16. Well, that's 6 over 4, or 1.5. To find T-star, the degrees of freedom is 15. So that tells us that T-star is equal to 1.75. Looking in the column for 0.90. So then our confidence interval is x bar, which is our sample statistic, plus or minus T-star times the standard error of x bar. So x bar is 76, plus or minus T-star, which is 1.75, times the standard error of x bar, which was 1.5. Remember that you do this part first. And on the lower end, we end up with about 73.4 to 78.6. And it'll be pretty smart to pause me right now and make sure that you can actually get that number. I did do some rounding, but just double check that you get something awfully close if you do the math yourself. Now in this example, note that what's changed is the confidence level. We still have the same sample mean, we still have the same standard deviation and size, just all that we've changed is the confidence level. So, and also just think to yourself that if the confidence level goes up, the multiplier is going to get bigger, which means your interval is going to get wider because the thing you add and subtract will have gotten larger. Okay, so the standard error of x bar is still s over root n, and those numbers haven't changed, so it's still 1.5. Our degrees of freedom is still 15. But now, because we're looking at 95% confidence level, our T-star is bigger. It's 2.13. And that was looking at the 0.95 column of that table. So our confidence interval is 76 plus or minus 2.13 times 1.5, which is 72.8 to 79.2. Notice that higher confidence level implied a wider confidence interval because the multiplier was larger. So it's really good to know the relationship between the width of the confidence interval and sample size as well as the multipliers. So let's just put that stuff down a little bit more formally. So as the confidence level increases, keeping the degrees of freedom the same, the value of your multiplier, or T-star, increases. You can see this by looking at that table 8.2 and just going across a column as the confidence level goes high, or across a row, sorry, as the confidence level gets higher, the T-stars get bigger. And if the T-stars are bigger, that means you're adding or subtracting a bigger number, which means the interval's width increases, i.e. gets wider. And as the value of the degrees of freedom increase, keeping the same confidence level, so now we're looking at going for a fixed confidence level going down a column, the value of the T-star multiplier decreases, and this is because that sort of variability or uncertainty decreases. The larger your sample, the more certain your average is more correct. And the larger degrees of freedom makes smaller values of T-star, which gives a more precise or narrower interval. Now there are a couple things you should check before you use this confidence interval procedure. So the first thing is the population of measurements probably should be bell-shaped, which you can check by doing like a histogram or graphing them. And a random sample of any size is measured. For really small samples, the data shouldn't show any extreme skewness and shouldn't contain any outliers. Also, this is for if you have a sample of any size, including sizes that are pretty small, but also it could be the case that you have to measure a large sample, and the arbitrary definition of large is an n bigger than or equal to 30. And in that case, it doesn't matter if you have skewness or anything like that. A big enough sample takes care of the skewness. But if there are extreme outliers, it's better to pick an even larger n. So each man in a random sample of 9 men between the ages of 30 and 39 is asked to do as many sit-ups as he can in a minute. The mean number of sit-ups was 26.2. It's a marathon number of sit-ups. And the standard deviation of the number of sit-ups is s equals 6. So first find the standard error of the sample mean. So SE of x bar, remember that's s over square root of n. So 6 over square root of 9, which is 6 over 3, which is 2. And what this tells us is that if we take many samples, so over many samples of the same size, so of size n equals 9, the standard deviation i.e. the variability, I think I spelled that wrong, variability of the means of these samples is about 2. And really the kicker here is that all the samples are of the same size, and it's the standard deviation of the mean that we're approximating. Find a 95% confidence interval for this mean. So remember that the general form of that confidence interval is x bar plus or minus your multiplier t star times the standard error of x bar. And we know the standard error of x bar is 2. We now just need to find our t star. So notice that the degrees of freedom is n minus 1, 9 minus 1, which is 8. And if you look at this table, 8.1, go to the degrees of freedom equals 8, and go across that row until you get 95% confidence. Your t star value is 2.31. So our confidence interval is 26.2 plus or minus 2.31 times 2, or 26.2 plus or minus 4.62. And 26.2 minus 4.62 is about 21.6. 2 on the upper end, 30.8. I did round those a little bit, but you know, if you have a more exact answer, that's fine. All right, write a sentence that interprets this confidence interval in the context of the situation. So let's start by saying our confidence level. So with 95% confidence, the average number of sit-ups a man can do in 1 minute in a sample of n equals 9 men is between 21.6 and 30.8. In this next example, we're going to look at how we can use confidence intervals to distinguish between two different groups and check and see if something different is actually happening in them. So volunteers who had developed a cold within the previous 24 hours were randomized to either take zinc or placebo lozenge every 2 to 3 hours until their cold symptoms were gone. 25 participants took zinc and 23 took the placebo. The mean overall symptoms for the zinc group was 4.5 days. That's how long they had a cold. And the standard deviation was 1.6. For the placebo group, the mean overall duration was 8.1 days, and the standard deviation was 1.8. So the question we'd like to answer is this mean of 4.5 really different from this mean of 8.1? And we're going to answer that using confidence intervals. So first we'll find a confidence interval for the mean overall duration of symptoms for the zinc group. So for the zinc group, notice that the sample size was 25. So the degrees of freedom is 24. And the T star that we use is 2.06. We also need the standard error of x bar. So that's S over root n. Well, S is, for that group, it was 1.6 over root 25, which comes out to be 0.32. So our 95% confidence interval is x bar plus or minus T star times the standard error of x bar. Okay, well that x bar, in this case, the mean length of cold was 4.5. Okay, and this comes out to be 3.84 to 5.16. So you'd expect the mean length of cold to last, or the average mean length of cold to be between 3.84 days and 5.16. All right, next let's do the same thing for placebo. So here our sample size was 23. So the degrees of freedom is 22, giving us a value of T star that is 2.07. The standard error of x bar, S over root n. Well, in this case, the standard deviation from the sample was 1.8 over root n, which is root 23. This comes out to be approximately 0.38. And so our 95% confidence interval is given by 8.1, which is our x bar, plus or minus 2.07 times 0.38, which is 7.31 to 8.89. All right, so in this case, we'd expect the mean duration of cold length to fall between 7.31 and 8.89 days. So now, on the basis of the intervals that you found in A and B, is it reasonable to conclude that taking zinc lozenges reduces the overall duration of the cold more than taking a placebo? So because those intervals don't have any overlap, on average, their means appear to be different. So yes. So yes, the intervals do not overlap. So the mean length of cold for the zinc group is 3.8 to 5.2 days, which is entirely below the mean of the placebo group, which was 7.3 to 8.9 days. As these intervals do not overlap, this suggests the means are actually different. And the final thing is, in the paper, the researchers say that they checked whether it was reasonable to assume the data were sampled from a normal curve, and they decided that it was. They probably did this using some type of histogram. And they got that their data was, more or less bell-shaped-ish. Not perfectly, but pretty good. And then how is this relevant to the conclusions? Well, the kicker here is that your samples, your two different groups, had small-ish sample sizes. So since the sample sizes were sort of small, you need to check and see if this holds. So that's kind of what I need to say. So for small samples, and it's a bit arbitrary, but remember that small is less than 30. It's necessary to verify that the population has a normal distribution. Next, we're going to talk about how to find confidence intervals for populations of mean of when you have paired differences. And so this is a special case of the single mean of a population, just kind of like what we're doing. And this occurs when we have two quantitative variables that are collected in pairs, and we want to know about the difference. So the first thing is that for your data, you have two measurements for each individual, and you find the difference by taking the first variable minus the second variable. So the population parameter, mu sub d, is the mean differences for the population. And this means that you take the differences then average. The sample statistic, instead of x bar, we just use d bar to sort of emphasize that these things came from differences. And this is equivalent to taking the mean of the first group minus the mean of the second group. Now the difference comes in the standard deviations. So the standard deviation of the sample is S sub d. And the way that you find that is you take the sum of the individual differences minus the mean squared over n minus 1, and then take big old square root of that. The standard error, so SE of d bar, is just S sub d over square root of n. And then the general form for the confidence interval is d bar plus or minus T star times the standard error of d bar. So it's very much just like the same thing as one mean, except for the thing that you're meaning is the differences. So let's do one example where we've been given the data sort of pre-processed, and then we'll do one example where we have to make the differences and do all of the steps. So a researcher wants to know whether the mean weight of the second baby is higher, lower, or about the same as the mean weight of the first baby for women who have had at least 2 children. She found a representative sample of 40 women who had at least 2 children and found that the mean of the difference, so i.e. first minus second, was 5 ounces. And the fact that this is positive means that that first baby was a bigger number, i.e. heavier. And the standard deviation was 7. Notice if this difference was negative, like 5 minus 7 is negative 2, that means the second baby was bigger than the first. Not that there was a negative difference. So write the mean of 5 ounces and the standard deviation of 7 ounces using the appropriate notation. So the thing is that this is a mean of differences, so the appropriate notation for that 5 is d bar, and the appropriate notation for 7 is S sub d. Find a 90% confidence interval for the parameter that you just defined in part B, and then write a sentence that interprets this interval. Okay, so first, T star. Well, our n is equal to 40, so the degrees of freedom is 39, and that's not on the table explicitly, so we'll just use that that's about equal to 40. So the T star that we find for 90% confidence is 1.68. The standard error of d bar is S sub d over square root n, so that's 7 over square root of 40, which is about 1.12. And then our confidence interval is d bar plus or minus standard error of d bar times your T star. So the d bar, the difference was 5, plus or minus 1.12 times 1.68. which comes out to be 3.12 to 6.88. So then we say with 90% confidence, the mean difference between first and second born is 3.12 to 6.88. And be a little bit more specific, meaning who is bigger, meaning the first child is on average 3.12 to 6.88. This was ounces heavier. Draw a picture illustrating the confidence interval that you found in Part C. And using this picture, would you conclude that the mean birth weights for the population are likely to differ? As in, is it true that the first baby is actually different than the second? So the picture that we're looking at here is just kind of like a number line with the confidence interval above it. So we have 2, 3, 4, 5, 6, 7. And the confidence interval runs from a little bit above 3 to a little bit below 7. And there's our 90% confidence interval. And the mean birth weights are going to differ. Well, it's easiest to think about that in terms of what would they be if they were the same. So if they were the same, first would equal second, which means the difference would be 0. And notice that the difference being 0 isn't included in this confidence interval. So yes, as 0 is not included in the interval, and this suggests that the birth weights do differ. Just a note, if 0 had been included, then 0 is a plausible value, but not guaranteed. I.e., if your interval had gone from something like -2 to 2, for example. I mean, in this case, you could say that, well, 0 is a possibility, but I don't know if it's 0 or if it's 2, so we just can't say that the birth weights are different. That's all. You just can't conclude for sure that 0 is the value if 0 was included. Now, that previous example had a lot of pre-processing done to it before. Like, it found you what d bar was, and it told you what the standard deviation was. And I'd like to go through an example where you actually have to do those calculations yourself. And it's a little bit tedious, but we'll get through it. Okay, so we have a random sample of 5 college women. They were asked for their heights and their mother's heights. And the researchers want to know whether college women are taller on average than their mothers. So here are the pairs, and the first thing we have to do is find the differences, which I'm going to call the D's. So for pair number 1, and for these we're going to do daughter minus mother. So daughter minus mother. So for pair 1, 66 minus 65 is +1. Pair 2, 65 minus 62 is 3. Pair 3, mom is taller. 64 minus 65 is -1. Pair 4, kid's taller by 3 inches. And last one, also kid's taller by 3 inches. So the parameter of interest that we care about here is, so the parameter is mu sub d, which is the difference in daughter height and mother height. One thing to note is that since it's a parameter, this is the population value, and the population value is not the d bar, it's the mu thing. So let's try to estimate that population parameter with 95% confidence interval. So the first thing we have to do, so I have many steps, I write these down, is find the sample statistic, which is d bar. So d bar is the average of the differences we found above. Well, that's 1 plus 3 plus -1 plus 3 plus 3 divided by 5, which is 1.8. So we estimate that on average, maybe hopefully on average, daughters are 1.8 inches taller according to this sample. Next, we have to find the sample standard deviation, which is given by the sum of di minus d bar squared divided by n minus 1, and then big old thing square rooted. So writing down what that is, big old square root sign. We take our sample values minus the mean, square them. So first we have 1 minus 1.8 squared. Then we have 3 minus 1.8 squared. And then negative 1 minus 1.8 squared. Then we have 3 minus 1.8 squared. And 3 minus 1.8 squared. All this divided by n minus 1. So 5 minus 1, which is 4. Now you should verify that you can do this yourself, because being able to do the calculations is also important. But in my numerator, I get 12.8 divided by 4. And this comes out to be approximately 1.79. Okay, next we need to find our T star. So T star, because our sample size is so small, the degrees of freedom is 4. And so the T star is 2.78. Okay, and now we're at the stage we were at in the previous problem. Well, at least at step 2 we were. So the next thing we do is find the confidence interval. And well, we have T star for that, so we're good. We also need to know what the standard error of d bar is. Well, that's s sub d over root n, which is 1.79 over root 5, which comes out to be approximately about 0.8. And so our confidence interval is d bar plus or minus this T star times the standard error of d bar. So the d bar that we found was 1.8 plus or minus this T star of 1.79 times 0.8. Well, the 1.79 times 0.8 is 1.432. .8 minus 1.43 is 0.37 to 1.8 plus 1.43 is about 3.23. So using that interval, write a sentence or two about the relationship between mother's heights and daughter's heights. So with 95% confidence, daughters are between, we'll say on the low end was 0.37 to 3.23 inches taller than their mothers on average. It is pretty important that you say on average, because this is a statement about the average differences between the two groups. So explain 2 things the researchers could have done to obtain a narrower interval. Well, a really obvious thing they could have done is they could have increased the sample size. And the main reason that this exercise kept the sample size small is, well, it's because it gets really tedious to have a bigger sample size. And what this will do is this will, in general, decrease the standard error, which makes your CI narrower. And the second thing you could do, which is not very recommended, is you could decrease the confidence level. And that's because, confidence level. And what this will do is this will come from a smaller multiplier. And that smaller multiplier implies a narrower interval. Although in general, the better of these things to do is definitely this guy.